from Google AI Perception, which is part of Google Research. And I'm here to talk about MediaPipe, which is a framework for live perception. And so MediaPipe is used to power applications that perceive the world around them. So these are some examples of applications that perceive the world around them. On Android, there are several apps that make use of machine perception technology, such as Lens. I think when you open Lens inside the Google camera, there are several kinds of objects that can be recognized by Lens. You also the MediaPipe framework runs fine on iPhone also. It even runs on the web using WebAssembly. And the MediaPipe framework is incorporated into the Nest Cam and Nest home device. And we have examples of the MediaPipe framework running on micro devices such as the Raspberry Pi and Google's Coral Edge TPU. That's a 10 TensorFlow processing unit. So I'll try to explain what the MediaPipe framework is for. So MediaPipe is for building perception inference pipelines, and so this doesn't include the training of machine learning models, just the inference, the series of events that have to happen during inference in your application or on the device. So MediaPipe it is designed to be cross-platform. And the reason for that is we want people to be able to develop machine learning models and apps wherever that's most convenient, for example, on a desktop machine, and then to be able to easily deploy those models onto the devices that their customers are going to use, like mobile devices. And MediaPipe is now open source, right? This is something we're very happy that we're able to do, to make MediaPipe open source in the last year or so. And so I say the reason for making MediaPipe open source is, one reason is it's one of Google's contributions to democratizing AI. We would like to make machine learning technology available, easy to use by a wider range of people. Another reason is that MediaPipe acts as a channel for publication for Google's research teams. So research teams naturally want to publicize their work. Google research teams, if they build something like an adaptive video reframing technology, they want people to see that, right? And so one way they can do that is to make that technology available as a component in MediaPipe, make it available through the open source repository MediaPipe. And of course, another way they can do it is to publish it in a journal. Again, having the open source release of their code in MediaPipe is a nice way to make the source code available around the journal. So here are some examples of where MediaPipe technology has appeared in public. I think that the first two examples show like advertising technology. Like the lipstick try-on, that's supposed to be an interactive advertisement where you can actually kind of judge how some makeup is going to look on your own face. So this is an example of augmented reality, which is done in real time. So we're streaming the video through, for example, through a webcam, and then the machine perception is identifying first of all detecting a face, right, and then identifying landmarks on the face, and then using those landmarks to decide exactly where to make a color change, right, that is going to mimic what the corresponding makeup would look like. The second example was an advertisement for the TV show Stranger Things, where on a mobile device a person could sort of see themselves inside the episode, right, or inside the world of Stranger Things. And this uses segmentation, right, to segment the exact boundaries of the person's face, right, so that they can be superimposed on the Stranger Things world. And another example like that is the lens living surfaces, where if we detect a certain page in a magazine, we can superimpose the video, so we can make that page in the magazine, actually move. So as long as someone's looking at the magazine through their cell phone camera, right, they'll see the live moving page in place of the static page. So inside Google, right, MediaPipe technology has been used in several places. YouTube was one of the first clients for this perception pipeline, and it's used in YouTube basically to view all the video that comes in. There's, of course, YouTube has way too much video for humans to view all of it, at least inside Google. And so the machine perception technology is used to identify characteristics of the videos that come in. For example, identifying a key frame, which would make a good thumbnail for the video, or identifying video which has a copyright infringement or objectionable content. Lens, as I mentioned, right, in Android, the Lens app, uses a machine perception through MediaPipe to identify things like receipts and signs that can be scanned and translated. And then it's used in some hardware from Google, right? It's used inside the Nest Cam to recognize things like the presence of people in a room, and it's used in the Nest Home device to allow some interaction with the people in the room. And then it's also incorporated. MediaPipe technology it powers some of the cloud services that Google sells through Google's cloud services. Okay, so for most of the presentation, I'll walk through an example of a perception pipeline and how you would use MediaPipe, right, to build up that pipeline. So the goal we want to do is to do this job, right? To have a video which includes some human hands, and to identify the landmarks on the hands, right, which are basically all the fingers and the palm of the hands. So this is the output we want, and the starting point is a researcher, right? You trains a neural network, right, to say, is it even possible for a neural network to recognize those landmarks? And so that means having a bunch of images, right, which are typically video frames, and then the corresponding manual annotation of where the landmarks are. And so we found, we can train a model that actually does that pretty well. For the training data, in the training data, the hand is always front and center, right in the middle of each image. So that's where the neural network works really well. But turning it into deploying it, right, so it actually works on devices, it takes a little more work than just building a neural network. But if we were to deploy just a simple neural network, right, we would do it in this way, right? We'd have a very simple perception pipeline. The perception pipeline just does some image transformation, maybe it downsamples the image to a size which is appropriate for the network, converts the image into a tensor in some representation, then it invokes the neural network, and that would be done using TensorFlow. So the TensorFlow is linked to MediaPipe. And then when you get the landmarks out, right, we have to convert them into a data structure which can be rendered, and then one of the things we could do is to render those landmarks at the way you saw, like as lines or dots, so you can see how well they align with the actual video. And these are all the steps that kind of very simple perception pipeline would have to do. So if you're going to use MediaPipe for this, all the steps in the yellow box, right, would be included in the MediaPipe pipeline. And so the boxes in the MediaPipe pipeline are called calculators. They're written in C++, and each calculator is basically a processor for a stream of time series data. Each calculator declares a public interface, right, which consists of the names of several streams of time series data for input, and the names of several streams of time series data which are the output of the calculator. Each calculator follows a life cycle which consists of an open call where the calculator is able to initialize itself, repeated calls to process, one call to process for each time series data point, and a call to close where the calculator can, well, free up resources, but also can produce a summary of all the data it's seen. And so built-in calculators are the calculators that are included with the MediaPipe distribution. So this includes the basic the basic neural network engine, right, which is TensorFlow, and it also includes the basic feature extraction calculators, image processing calculators to pre-process images from video, and then some output calculators to do visualization or rendering of the output. One key characteristic of MediaPipe is the way that the data is collated. All the time series data that enters MediaPipe is tagged with timestamps. So those timestamps indicate the time at which that data was recorded in the world. And the data is initially collated according to timestamp, right? So each calculator gets a process call with all of its input streams synchronized to the same timestamp. And this is typically what you need, what you would like to interpret a particular image, right? Is all the data which was coincident with it in time. But the calculators do have memory, so in case you need some sensory data from the recent past, the calculator's memory can be used to keep that data available. So this simple graph is simple enough that it's fairly readable as it is. But larger graphs, it becomes helpful to be able to group calculators together into what we call a subgraph, which has the same interface as a calculator does, right? It accepts a set of named input streams of time series data, produces a set of named output streams of time series data. So you can use a subgraph in place of a calculator inside of a MediaPipe graph. And this is a way to organize MediaPipe graphs so that they're more readable. And we found that they quickly become unreadable. So if we use the subgraph to organize a very simple perception pipeline, we wind up with just two components: the hand landmark subgraph, right, which does all of the neural network conversion and execution, and then the renderer, right, which takes the landmarks and superimposes them on some video. So the issue with this solution is that the landmark detection is pretty expensive, right? And so if you run the landmark detection over whole video frames, it actually takes a second, right? And you only get a few frames per second output. And so the hand landmark neural network runs much better if it has a region of interest, which is limited to just the area around the hand. And so one technique that can be used to speed up the inference is to first do palm detection, which is a relatively lighter weight task, right? This identifies the presence and position of the hand, and then use that as a region of interest. So this becomes the optimized MediaPipe graph. So the first thing that's done is palm detection, then we get the rectangle for each palm, and we use that as a region of interest for hand landmarks. And then hand landmarks runs on a much smaller set of data, and it runs much faster. So this is a good optimization, but it's still a little slow because we still feed the whole image into palm detection, right? And palm detection, even though it's faster, it's still slow and runs over the whole image. So another technique that we can use is, because video is pretty continuous, right? If we have a region of interest for the previous frame, we can use that as the region of interest for the next frame, and that actually works pretty well for most video. And so if we have only our landmark detection hand landmark calculator, we can use its previous landmarks to produce a region of interest for the next call to the hand landmark. And so this works actually really well. This is a very fast implementation because it's always operating on a limited region of interest. The only time it doesn't work well is for the initial frames, right? When the video first comes in, we don't know if it has any hands at all or where the hands are. And so it winds up scanning the whole frame. What we technically do, right? We call the hand landmark neural network with a large frame, and that's relatively slow. And so there's one more trick that we can use, right? Which is to combine the palm detection together with using the previous region of interest. So on the first frame, we initially do palm detection, and then we use that to limit the landmark detection. And then on successive frames, we use the the previous landmarks to derive a region of interest that it's a hint about the region of the hand for the next frame. And then if the hand landmark for some reason fails, right? For example, the hand has become obscured or is out of the video frame, then we wind up running hand or palm detection again whenever the hand comes back into frame. So this is just an example of how having a framework for composing an algorithm from components can make the job of optimizing algorithms more feasible. And then when we showed this, we showed the hand detection in two places actually, right? At a conference and then also on the Google AI blog. And people were really excited about hand landmarks. But one thing they asked is, can we detect both the two hands at once, right? And the answer was no, right? Because it had been trained, as you saw, right? It was trained to recognize a single hand. And so, but all the same techniques which are used to optimize the single hand detection can work with the multi-hand detection. But it becomes yet more complex because we have now a set of regions of interest that need to be communicated from one frame to the next frame, and we have a much more complicated criteria for when do we need to do palm detection, right? We have to detect when a new hand has come into the frame or when no hands are in the frame. So there's yet more logic, right, in a MediaPipe graph, right, which is doing multi-hand detection. Yeah, as I mentioned, we published or mentioned this hand landmarks on the Google AI blog, and that got a lot of attention and a lot of excitement. It was in, I think, like some journalists, right, were right away curious whether this can be used to do sign language, right? That was like a concept that occurred to people right away. Okay. So one of the main things that was done with hand detection was optimizing it, right, so that it could run at a high frame rate. And this is one of the issues that the MediaPipe addresses, right, is trying to provide good performance, right, on a wide range of devices. So one of the main techniques here is GPU acceleration. TensorFlow is already set up, right, to run on CPUs or GPUs. And MediaPipe reflects that, right? MediaPipe has components that run on CPU and components that run on GPU. And so it's possible to use GPU strategically, right, to make a MediaPipe inference pipeline run faster. Another feature for performance is the executor. An executor is essentially a thread pool, a set of CPU resources, CPU cores, which are going to be assigned to specific calculators in the graph. And this can be used to assign special resources to some calculators which need those special resources. Okay, so given the solution, right, the graph which actually does hand tracking well, that piece of work can be reused and extended in a couple different ways, right? So one way to reuse it is to substitute a different kind of feature, a different kind of landmark detector in place of the hand landmark. So in this case, we just replaced the hand detection and hand landmarks with face detection and face landmarks, and then the same graph is doing face landmarks and face tracking, right, instead of hand tracking, and so the result looks like this, right? So we're able to identify all of the landmarks on a person's face. Another way to reuse the hand detection or hand tracking inference pipeline is to use its output, right, to do a new job, right? So the idea here is to take those hand landmarks and to recognize gestures, right? So we can train a neural network whose input is a very small data set, right, of a very small number of features, right, one for each finger, and then output a gesture label. And so we've trained this, and this seems to work pretty well. And yeah, so you can imagine, right, that it can identify these geometry of hand landmarks and turn them into gestures. Another way to use hand landmarks is for effects, right? Similarly to how we can use the face landmarks for makeup effects, we can use hand landmarks for hand effects. And that's an example here. Okay, and so the final thing I'll talk about is the technology inside the MediaPipe framework. So this chart kind of depicts the MediaPipe tech stack, and the horizontal axis shows different platforms, right? Like Android, C++, and TensorFlow as different platforms. The vertical axis shows layers of dependency. And then the light to dark gray axis shows levels of granularity. So you can see that the framework is implemented mostly in C++, and that's our main technique for cross-platform support, right? Is we keep the framework pure C++ and we can just compile it on various platforms. There's a small set of utilities which are platform specific for things like Android and iOS to help out with diagnostics on those platforms. And then there's TensorFlow, OpenCV, and Eigen as they're their own cross-platform environments, and we depend on those. And then the calculators, the built-in calculators, as I mentioned, are mostly pure C++, and so they're portable to essentially to all platforms. The MediaPipe distribution comes with a set of example graphs, and also I should mention that the APIs that the MediaPipe exposes are these graph execution, graph construction, and calculator API, right? So you can the simplest thing to do is to take a prepackaged graph, such as the hand tracking graph, and just run it, right? You can run it inside your application, use its output to do some rendering or something. The next level of interaction you can have is to author your own graphs, right? So that's the graph construction API. And the basic format, the most popular interface there is the Post protocol, right? So you just specify the graph, you specify the set of components and their options and their connections, all using protobuf, which is a lot like a JSON data structure. And then the most interaction you can have with MediaPipe is to write your own calculators. So if you have a new machine learning algorithm or a new rendering algorithm, you can implement it as a MediaPipe calculator. You can use it yourself, and then if you're really generous, you could contribute it, as open source and include it in MediaPipe. So here's where to find MediaPipe. If you go to MediaPipe.dev, right, that'll take you to the GitHub repository for MediaPipe, and you'll find all the source code there. You'll find all the demos, including the hand tracking demo, and then in order to use MediaPipe, you just have to clone the repository and build it from scratch on your workstation. Another thing you'll find is our documentation. It's pretty standard. It accompanies the repository. Another thing you'll find is this viz.mediapipe.dev. This is a MediaPipe configuration visualizer service, right? So it's just a service hosted on App Engine, on Google's App Engine. And the first thing it does is you can, if you paste in the description of your graph, right, in protobuf language, you'll see a rendering of the graph, right? So you can discuss the graph. And inside Google, what we found is that people use this very frequently, right? They very rarely will communicate about their MediaPipe configurations as protobuf, right? They always want to point to the graph visualization of it. And then this visualizer has a few other functionalities too, right? You can use it to profile a graph, right? So if you run your MediaPipe graph and you enable profiling, you'll get a profile file, which you can also paste into this visualizer. And when the profile file will show you the whole series of events and just how long they took in microseconds. And it'll connect back and forth between the graph view and the timeline view of the execution of your graph. So it can be used to kind of review the way that a graph was running on a device. And then the third thing that this visualizer can do is you can actually run the graph in the web browser. We have some people on our team who made a translation to WebAssembly. So it'll take a certain set of MediaPipe calculators and compiles them into WebAssembly JavaScript code, and then it will actually show the running graph in the browser. And yeah, and we can even try that here if we have time. So if you go to the repository, you'll find several examples, maybe about 10 or 20 examples, and yeah, in each one of them, there are a lot of them that are actually graphs written specifically to run on a mobile device. Some of them are designed specifically to run on desktop instead. And ideally, these graphs will run on all the platforms, right, without change. At the moment, there are the calculators are not all completely cross-platform. So there's sometimes a substitution is needed in order to make a graph that was designed to run on desktop to run on mobile. But we're working on that, right? And we hope that soon MediaPipe graphs will run every MediaPipe graph will run on every phone. So to keep track of development of MediaPipe, you can find updates on Google's developers blog. You can also find an occasional mention of MediaPipe on Google's AI blog. And then you can find the series of releases of MediaPipe at MediaTypeDev, right, which is the GitHub repository. Okay, and so I could pause for questions. Yeah.
Yeah. So like when you write the code like C++ code with the intention to be used in different platforms, are there constraints in like mobile platforms in terms of processing speed or storage?
Yes.
Like what's the cost of developing kind of like one application across different platforms?
Yeah, it's a good question. Yeah, so the performance characteristics are totally different, right, between desktop and mobile devices. And so typically, and I've seen research teams inside Google do most of their development of the models that they want to deploy on desktop, just because it's quicker, it's faster for them to work there. And then they'll set up an environment which is as close as possible to the device that they're targeting on desktop. And then eventually they need to port that work to mobile device. And there are different constraints in terms of the, one constraint which has been emphasized to us is the power constraint, right? So not only that the mobile device has more limited bandwidth for processing, but it has a much tighter budget for power. And usually power is the limiting factor. So even after teams will have a graph successfully ported to a mobile device where it actually looks like it's working, the product teams will say, no, we can't include this right in the product because this doubles, the power budget, right, of the product. And so we actually need it to be much more efficient, right, to where we could actually include it in the product. And I know that inside Google Research, there is a team that specializes in doing power profiling on mobile applications. And the MediaPipe team is sort of partnered with that team. But we don't have any power profiling available in the open source edition yet. Over here. Yeah, so I think that there are some services. I think like Google has a cloud image service that Google sells. And I think that that image team partners with the MediaPipe team also. So they actually use MediaPipe technology in some of the image cloud APIs. And so, yeah, so there is a cloud offering related to MediaPipe. And in fact, I think that Google is interested in making a tighter connection there, right? To where customers would be able to make a MediaPipe graph and run it, directly in a Google Cloud service. But Google doesn't actually have that cloud service available yet, right? So that's a future development.
For the depend on points, do you have an interface to extract which point is related to the points? For example, I have this pinky and which point is related to the pinky points and the drops of the pinkies?
Yeah, I think that the hand landmarks, similar to the face landmarks, they have unique identifiers, right? So there's a like, I think it's essentially a sequence of landmarks, and the tip of the pinky is always the very last landmark in the sequence. So they're uniquely identified by which joint they refer to.
Also, they're in an order.
Yeah, they're in an order. It's essentially like an enumeration, right? And it's an exact number, right? They're always I don't know the exact number. It's always 22 landmarks.
So for the gesture recognition, do you put both image and the landmarks or just put the landmarks to recognize those?
Yeah. So for the work we've done with gesture recognition so far, we've only sent the landmarks to gesture recognition, and I think that's how we'd like it to work, right? Assuming that it's the performance is acceptable, right? Then we'd stick with that as the interface to the gesture.
Is that a network or just for this gesture recognition part? Is it a network or is it a linear machine?
No, it's a neural network also. I think both the hand landmarks and hand gestures were TensorFlow models. The guy who built the models works closely with me, but I don't know exactly which operations he uses TensorFlow.
So for the performance optimization, how do you drive? What kind of measurements or metrics do you get, and based on that,
Yeah. So I think that the metric that most people see, I think what people see in live inference, right, is two things, right? They see a lag and they see a frame rate, right? And so those are two things which we are able to measure and report. So the lag is tells us the end-to-end latency, right, across the graph. The frames per second is determined by, I guess, that end-to-end latency divided by the amount of pipeline, right? And yeah, those are two things that are measured. And one type of calculator component that we have available in MediaPipe is a calculator component for flow limiting. And this seems to be the single most important tool that we have for making models run acceptably on devices. So flow limiting is just measures the number of calculations in flight, right? The number of frames that are in flight, and limits that to a fixed number, typically to one frame in flight, or maybe 2 frames in flight. And so the idea, what happens there is that as additional video frames come in, if the graph doesn't have enough capacity to process those frames, we have to drop those frames. So when the graph is capable of accepting another frame input, we always use the most recent frame, right? And we don't allow the graph to get behind in past frames. Yeah.
So for the fault detector, I noticed the detection box is not just a rectangular related to the scale of the image. So what type of detector are you using?
Yeah.
How do you create that box related to the angle of the ball?
Yeah, it's a good question. I actually don't know the answer myself. I do know that our rectangle data structure, right, has not only the bounding box coordinate, but it has an angle also.
Yeah.
So we have a sort of a rotated bounding box data structure, which is being used for bounding boxes. And I think that data structure may have come out of Google's previous work with stabilization, image stabilization. So the team that I work with has a history in the area of image stabilization, and for advanced image stabilization, it's necessary to track objects in order to align successive images in order to do stabilization. And so bounding boxes around those tracked objects are part of this stabilization technology. And so I think that the bounding box representation may have carried over from that. But I don't know the details of how palm detection uses the bounding box.
Thank you.
Yeah. Yes.
I was really intrigued by the use of palm detection because it was faster as a feature group.
Mm-hmm.
You know, I'm curious what considerations you made when selecting something like that. How sophisticated of a policy you can make in MediaType around choosing to execute a more expensive stage of the graph, you know, under certain conditions.
Yeah, that's a great question. And I think that is actually the area where I see MediaPipe adding the most value, right? Is in being able to add logic, you know, manually engineer logic into an inference pipeline to make use of alternative techniques and under alternative conditions. And one place where I've seen that used there's the team that has been researching the capabilities that the Google Home device could have, right? That team has done a lot of really sophisticated machine inference pipelines, and I've noticed that they have that they will, for example, they will parameterize some of their models with the number of objects that they can be detected, right? So if the model is limited to one object, right, it will run relatively quickly, right? If they're allowed to detect up to 10 objects, it can run slower. And so they actually have some tuning of the model based on the performance of the device, right? So if the device is not keeping up, they'll adjust the parameters to the neural network so that the neural network is limited to outputting a smaller number of detections. Oh, in the back.
So in the use of, you were saying before that more readily sacrifices framework for latency. So when you drop frames, does that affect the algorithms that you use for these frame differences like the tracking and stuff like that? And if that's the case, is there any compulsion for you to drop frames?
Yeah, that's a good question. So I think that a lot of the models that have been incorporated into MediaPipe begin as single image models, right? So they typically often work with just one image of data. And the models which work with multiple images are relatively less common. And so the frame dropping technique has typically been used on models which are processing only single image anyway, and so there's no interaction between the dropping of frames. And I think that if we had like these long-term, short-term memory models that we're running, which actually have an important history, we would have to be more careful about which frames we drop, and possibly, you know, making models that can tolerate, you know, the dropped frames. But I think that we don't have much experience with that yet, right? Because those models with memory are relatively rare in our suite. Yeah.
Did you experience much performance loss when putting that batch in? Like you're processing one frame at a time.
Mm-hmm.
What's the difference about that?
Yeah, it's a good question. Because one thing about MediaPipe is it was originally designed to run in batch mode, right? It was really designed for the YouTube use case, right, where it's running in batch mode. And so we've kind of retrofitted the framework so that it works in real-time mode. And we've added the flow limiter calculator, right, as part of that support for real-time operation. And yeah, so I think there is a significant there's a significant performance cost due to not running in batch mode. The throughput is significantly lower. But I think it's unavoidable, right? I mean, because when the application domain is real-time processing, the only thing that people care about is the lag and the frame rate, right? And so those are the metrics that we need to optimize. Yeah.
Does MediaPipe have audio support?
Yes, it does, and it has an interesting history. The Google's video machine learning teams and audio machine learning teams were historically, mostly separate, and so we have actually a whole set of video, video processing, video featured extraction calculators, and audio feature extraction calculators, and there haven't been many projects that actually combine the two and into one inference pipeline. And I think that the team that's working on machine learning for the home device, they've started doing that. Right? They started pulling in data that's audio and video data together. And MediaPipe, I think, is a good framework for doing that, right? Because it's built to collate all the data according to timestamps. So I think we have the right abstraction for how to bring that data together. But I have to admit that we have relatively limited experience in actually bringing the data together. Yes.
What are your next steps from MediaPipe?
Yeah, good question. So I think that MediaPipe has shifted, towards mobile, right? So mobile is a big initiative for MediaPipe, and I think that we're working hard now to make the cross-platform feature of MediaPipe more robust. So what we've done, for reasons of expediency, right? We've kind of allowed people to build calculators that are specifically for Android, right, or specifically for iOS, or specifically for server operation. And we're working now to make sure that more of those calculators are actually cross-platform. Make sure that all of our data types are cross-platform, and that the calculators, as much as possible, are cross-platform also. Thanks. Oh, so what time is it now? 43. So maybe I'll show. I set up here to run a demo quickly, so I'll try to run one demo. So I can show you this is the hand tracking MediaPipe graph that we saw. So it's running here. And this is unfortunately the single hand version, right? So it won't do multi-hand. And I set up to show off the latest. I think the latest demo that we made is autoflip. So autoflip technology is framing, automatic framing technology. The idea is, like in Facebook's portal device, right? That you want to be able to automatically keep the speaker in the center of the video. And specifically when you need to change the aspect ratio, when you need to change from a widescreen video to a narrow video, you want to be able to automatically detect where's the interesting part of the video and keep that in the middle. And then you want to conform to a bunch of constraints about how a camera should move, right? So that they jostle things. And so this is a MediaPipe graph that runs offline in batch mode. And that's the build. Let me see if I can run this. Okay. So here I'll try. We're running autoflip on a. So I'm running it on a skiing or snowboarding video, which I don't think this. Yeah. So and I'm not sure that autoflip works really great on this video, right? But I'll run it on it anyway. And so it's running through all the frames of the video and outputting a video which is reframed, dynamically reframed. So it's still working now. Okay, just finished. And then go over to find. So I need to find the URL. Okay, here. So this is the input frame, and then And this is it. This is the reframe video. So it tries to find an object, right, which is interesting, and then pan the virtual camera, right, to track that object. So I should have showed you the original video also, right? But so this is Google's reframing technology, applied to a video. And so the input video was wider aspect ratio, and the output video is a square aspect ratio. And this is one of the rare examples I've seen of a machine learning technology that has a very clear commercial use, because this has actually been used in Google to reframe advertisements, right? So we have like thousands of advertisements, right, which were fitted for certain screens, right, for desktop screens, right, in the days when that was the usual aspect ratio. And now people hold their phones vertically, right? And so those advertisements were almost unusable without this auto reframing technology. Okay, so thank you.